Dear student, welcome to my channel. Topic of this video is support vector machine. In this video, I am going to discuss soft margin SVM with parameters chi and c. Now let us start. SVM is mapped as a constant optimization problem. Main objective of SVM is to find a hyperplane, that is nothing but decision boundary, that maximally separates the two classes of data points in high dimensional space. Hard margin SVM. When the data is linearly separable, we can go for hard margin SVM. Now the SVM problem is nothing but maximize the margin. This is equivalent to minimize the norm of the weight vector subject to constraint. The optimization problem is expressed as minimize 1 by 2 square norm of the weight vector, and constraint is that all points should be classified correctly. So constant optimization problem is our objective function is to minimize this, but at the same time constant is that all points should be classified properly. Now see this hard margin SVM. Why it is called hard margin SVM? Because here two classes are there and they are sufficiently separated. So when we get this support vector and this support vector for this class, and in between we get the decision boundary, so distance is sufficiently large, so there is no problem. So in such cases we can go for the hard margin SVM, but most of the time in reality this is not the case. Now see, here the distance between the two classes is sufficiently large, so this particular can become the support vectors for this class. This can be candidate for the support vectors, and in between we can draw the decision boundary, and so sufficient margin we will get here. But this is not case with the case with such type of data. So here if we take the support vectors, then it may happen that they are very close to each other, so we will get a very less margin. So when less margin is there, at that time we may not get error for the training data, but in testing data we get a error, and the model cannot be generalized and robust for the future unseen sample. So when such type of data is there, it is better to go for the soft margin SVM. Now see, the equation for the hard margin SVM is yi wxi plus b greater than or equal to 1, but the equation for soft margin is same, yi wxi plus b greater than, but instead of 1 now it comes 1 minus sky I. Now sky I parameter is associated with every sample, and that denotes the penalty, soft margin, and this is the equation for soft margin SVM. Now see, two classes are there. For this class two support vectors are there, for this class two support vectors are there. Now in between the decision boundary comes, and this is nothing but the margin of the between the classes. Now this margin is sufficient, so here we will get the in future also we will get the good less number of testing errors. But here we can see that when we draw this boundary, this sample will come in front of this particular support vectors, this comes in front of the support vectors, so they will be wrongly classified, but still we will allow. So here the penalty is associated with each sample. So for these points which are behind the support vectors, the penalty is 0. So sky I value for this sample which are behind this is 0. Now for this boundary penalty is 0, but here afterwards when they cross this particular support vector boundary, at that time here the penalty is associated. Now we can see for the red, so this point is xj, so penalty is associated with sky j, so some value is there. If we compare the I point, so with I point also, that is xi point also, a penalty is there, but penalty of this xi point is more than xj. Now we will see for the blue class. Now for this we will get again the penalty, because this xk point, because they comes in front of the support vector, so again the penalty is there. For L point it crosses more, so penalty is again more, and this penalty is denoted by sky L. So now here we can observe that the points which are behind the support vectors, their sky value is 0, even on the support vector value is 0, but when the points comes in front of the support vectors, their sky value is associated. Now the question is, why not to draw the, because these points will come as a misclassification, so why not to draw the support vectors, or why not to choose this as a support vectors and this as a support vectors, or this as a support vectors and this as a support vectors. But if we choose either this or this support vectors, at that time we will get very less margin. So when margin is less, at that time training errors are less, but chances of testing errors are more in the future. So better here we can allow some misclassification, that is nothing but the soft margin SVM. That is during we will keep ensure that our maximum margin should be maximum, so that some misclassification errors occurs during the training time, but it ensures that as we keep the maximum margin, so in future when unseen sample comes, then that is nothing but for test error, the error will be, the total model will be success and the error will be less. Soft margin SVM, that is handling non-separable data, because they are very close to each other. When the data is not perfectly separable, slack variable, that is chi, are introduced to allow some misclassification while still trying to maximize the margin. The modified optimization problem becomes, this is the original hard margin, that is minimize this squared norm of the weight vector plus c is the parameter and summation 1 to n chi, because for every point chi is associated, but when the points are behind the support vectors or on the support vectors, the chi is 0, and when they crosses, then support chi value or penalty value increases. Now constant is instead of 1 here 1 minus chi. The parameter c is very important, which controls the trade-off between maximize the margin and allowing the classification errors. That is we will see the value as the value of c changes, how the margin changes. So it will be more clear with the example. Now the same constant will be remain same like hard margin. The SVM tries to minimize a quadratic objective function, that is squared norm of weight vector, and it is constant by the linear inequalities, that is correct classification with sufficient margin. Now we'll see one example. Total 10 points are there. In class 1 5 points are there, in class 2 next 10 points are there, that is from 6 to 10. We initially assume that c is a small, so margin is sufficiently wide, because when c is small we are taking the margin is sufficiently wide. So for example, just make assumption that point 1 to 3 are correctly classified, that is they are beyond that support vectors, not exactly margin but beyond that support vector line. So these are outside the margin and correctly classified, therefore chi variable for or slack variable for this variable is 0. Point 4 is misclassified close to the margin and towards the decision boundary, so this point is within the margin but on the wrong side, hence misclassified with a small. So for this point 4 some value is there, that is nothing but penalty is there, but that penalty is small. Now point 5 is misclassified because it is in present in another class, so this point is significantly far from the decision boundary and misclassified, resulting in the large penalty. Similarly for 6, 7, 8 they are classified correctly because they are behind the support vectors. For example, this is the class boundary, this is the class boundary, and these 6, 7 points are behind that class boundary, so their value is 0. Then for point 9, this is the support vectors for this particular class, and this point 9 comes in front of the support vectors, so some penalties associated, but still chi 9 is small. For point 10, so this is another class and this point is present inside this class, so that's why the chi variable value is 5 and the penalty is high. Now here the same conclusion, that point 1 to 3 and 6, 7, 8 the penalty is less. For 4 and 9 penalty is there but still it is less. For point 5 and point 10, as they are crosses each other boundary, so the penalty is high. Now if we take the large c and if we take the small c, what happens? Here we assume that c is small, so when c is small, at that time we can see this equation that as c is small, so penalty does not exceed up to particular limit, so we will allow the maximum margin. So here first we make assumption c is small, so margin is sufficiently small or sufficiently wide. So here when small c is there, this allows the SVM to tolerate more misclassification, focusing on the maximizing the margin, because whenever we maximize the margin, at that time some of the samples may come into this region and that results in the misclassification. This would lead to a larger margin but might misclassify some points. Small c is generally better for generalization Even if few misclassification occur, the SVM will draw a smooth, more general decision boundary that might ignore some misclassified points. And when we change C from small to large, at that time margin becomes narrow. So no misclassification during the training, but the classification errors chances during the testing will be more. This means SVM will heavily penalize large sky values and forcing the model to reduce the number of misclassification as much as possible. Large C force the model to attempt classify them correctly at the expense of the smaller margin. Large C tends to result in overfitting, especially if there are noisy data points, because large C try to reduce the margin between the two classes. SVM will draw a tight decision boundary that attempts to correctly classify almost all points during the training session. Now here this is the tentative for points 1, 2, 3, 6, 7, 8. They are behind that support vectors. So sky value is 0. So C small allow, C small allow. For 4, 9, the error is there. So for example, if it crosses the threshold, because when C is small, then that total penalty is again still less, so it will allow. But large C, because of this C is multiplied with this penalty values, so it will not allow. So it forces that the margin should be small. 5 and 10, they are in the opposite class. So here sky value is there, and it will, and the sky value is larger because they are present in another class. So this small C is also not allowed and large C is also not allowed. But still, because of this, it is accepting some points. So it tried to maintain the wide margin because C is small, so penalty value will not exceed like large C. So still it allows the wide margin and it allows narrow margin. So as wide margin is there, some misclassification occurs during the training, and here there is almost no misclassification during the training session. Now we'll see when C is large, so we will get the hyperplane like this, and when C is not too large, we will get the hyperplane like this. So when C is not too large, we are getting the maximum margin, and when the C is when C is small, we are getting the maximum margin, and when C is large, we are here see we are not getting margin, or margin is very narrow. So that is a problem. So in the next diagram it is more clear. See, when C is 100 and C is 10, when C is 10, we are getting wide, and here some points comes in front of the support vector, so they are misclassified. Here these 2 points will come, but when C is large, at that time boundary becomes very small. So in future it may happen that even if some of the point changes, they will come to the they will be misclassified. Now see, this is the Python programming output. 20 points are there. This point, some of the points belong to this class and some of the points belong to this class. So when C is 0.01, so at that time C is small, so margin is sufficient, and it still allows some misclassification of the, because this is the support vector for this, but still some misclassification comes. And here, now here as more misclassification, so we may change the value of C. Now see, when C is 0.11, now you can see that misclassification reduces, but at the same time margin is also reduces, but still it is acceptable, because if we use this C, more misclassification occurs during the training. But here this is, we can see that the margin is also maintained, at the same time misclassification errors are less. So when we increase C from 0.11 to 0.41, we are getting less misclassification error during the training, but the width is reduces. And see the 1.01, now here we can see that width is very small compared to our first C value. So as C is increases, the margin is decreases, but at the same time misclassification is reduces. So this is all about the soft margin SVM. So in practical application, we always go for soft margin, because based on C we can change the margin, which may be narrow or which may be wide. So depending on our situation or data, we can make the decision. So this is all about the soft margin SVM. Thank you.